All right, real quick investigation of polygons here. First off, how many degrees in the sum of the angles of a triangle? All right, well, we know that that's 180. We've known that for quite some time. So for number 2, we have trying to find the number of degrees in the sum of the interior angles for all the quadrilaterals in triangle ABCD. There's been a diagonal drawn here to separate it into two triangles. If you add angle 1 plus 2 plus 3, you get 180. 4 plus 5 plus 6 would also equal 180, and that's because they are both triangles. So pretty simple there. So if I take all three of the first three angles and the three of the second set of angles, I get 360 because I'm just adding the two together. So every quadrilateral must equal 360 degrees. All right, same kind of concept for a pentagon. From one vertex, draw all possible diagonals. So I'm skipping AB because that's already connected, and do AC and AD. AE is already connected. So I've got three different triangles. Each one of them contains 180 degrees. And within those three triangles, I have used all of the angles that are in the pentagon. So take that 180 times 3, the pentagon must have 540. All right, talk about a hexagon, do the same thing. Draw the three from any vertex you want. And it creates four triangles, each of which is 180. Total must be 720. Since we can't connect consecutive vertices, there's always going to be two fewer triangles than the number of sides in the polygon, and that's going to lead us to the formula for the number of degrees in a polygon. All right, so in example 5 on the next page, what we're looking at here is the number of sides in the figure followed by the number of triangles you can draw, which is always two fewer. If we multiply that number by 180 or just keep increasing it by 180, we generate this table. And so to generalize it, if it's an n-gon, any type of polygon, the number of triangles is two fewer. So the number of degrees is 180 times the number of triangles. So the pattern is sum of the interior angles, this is always for the total, not for an individual, 180 times n minus 2. And that can work both ways. Either I can plug in the number of sides, or if I want to know how many sides a polygon has, given the total number of degrees, I can put that on the left side and solve for n. All right, part 2. So we've got a regular pentagon, we've got a non-regular pentagon. And what we're trying to do here is, well, first off, describe what is required for a polygon of any kind to be described as regular. All sides and angles must be equal. Some of the measures of any pentagon is going to be 540 because I can split this pentagon into three triangles. I can split this pentagon into three triangles. Whether it's regular or not does not change anything about the total of all the angles in the pentagon. So to do any one angle of a regular pentagon, I could divide the 540 by 5 and get 108. And that's because if it's a regular pentagon, all 5 of those angles are equal, so it's okay to divide by 5. But if it's a non-regular pentagon, dividing by 5 doesn't make sense because they're not all the same. So I would need a lot more information to be able to tell what those angles are. All right, describe how to find the measure of each angle of a regular polygon. We're going to take the sum of all the angles and divide it by how many sides there are, because the number of sides and the number of angles is the same. So just divide by n, and that takes the sum and turns it into an individual angle. So we can do that for any one of these. So in the first column for each type is the total degrees in that figure, and then if I just divide by how many sides there are, so in other words 720 divided by 6, 900 divided by 7, and so on down the line, I can figure out what each interior angle is. Now, while the number of degrees in the polygon keeps going up by 180 every time, each interior angle, the amount it increases by, tends to slow down. So it's going up pretty fast at first, but then eventually, as I keep going up, the amount that it increases by is going to slow down, and it's going to end up to the point where as I get very large, this interior angle can never even get to 180, right? If it's 180 degrees, now it's a straight line and I don't have two sides to connect to the rest of the polygon. So it'll never get past 179 and change. It's gonna keep increasing, but only to a certain point. All right, now exterior angles, those are supplementary to interior angles, and that's not listed in this chart here. But to draw an exterior angle, what you do is you take a polygon and you extend one of its sides. Interior is here, exterior is on the extension. So because they're supplementary, we can figure out how many degrees there are. If I know that a single exterior angle on a regular polygon is this formula we just developed, 180 times n minus 2 divided by n, and exterior angles are supplementary, each exterior angle would be 180 minus the interior angle. So that's another way to write this, is 180 minus the interior angle. So I'm replacing the interior angle with its formula. If I do some simplification here, first distributing the numerator, and then dividing both parts of that numerator by n, then subtracting the 180s and distributing that minus, I get 360 over n. So what that tells me is the total for the exterior angles must be 360, and when I divide by n, I get each one. So the sum of the exterior angles is 360, always the case. And if you have a regular polygon, you can divide by n to figure out what each one is. All right, now you also, if you know the angle, you could divide by the degrees in the angle to get how many sides there are. That's another nice way to solve for the number of sides in a polygon. All right, so last part here, close to the last part anyway. For part 3, a central angle in a polygon, that's when we connect to a center point, just like when we did a central angle of a circle, same kind of concept. When we do this with a hexagon, we end up creating an equilateral triangle. So all 3 of these segments end up being equal. Would this happen if it were not a regular triangle? No, because the reason why it is equilateral is if I take 360 degrees and divide it by 6, my central angle is 60. This is an isosceles triangle, so these are also both 60 if I divide the remaining 120 equally. But if it were not a regular hexagon, I wouldn't know that's 60 degrees, and so those 3 angles wouldn't be equal. So it has to be a regular hexagon for that to happen. It can't even be a regular some other kind of polygon, because then the degrees at the top would change, which would change these two as well, and we would have an isosceles triangle instead of an equilateral. All right, so how many triangles of the same size are there? We can make 6 of them, because I can just keep on connecting to each of the vertices. There's going to be 6 going around the hexagon. All right, so keeping on with that same concept, describe how to find that measure. We just did that. We divide 360 by the number of sides. That's how we do a central angle. Came out to 60. Would that work if it was a non-regular hexagon? No, because again, if the side lengths are different, then the angles are different, and so we can't divide equally. And finally, this last part here, if angle 1 and angle 2 are both 60, which we discussed already, angle AFE, if I go back to the diagram, angle AFE is skipping over, right? So since all of these triangles contain 60s, AFE would be this 120 degree obtuse angle. And that turns out to be the interior angle of a hexagon. So if you don't draw any of these spokes, each one of those obtuse angles would be 120. And that summarizes what we need. We'll work more with these interior, central, and exterior angles in class.